So covalent bonding. Is that showing up all right?
Yep.
Okay, so covalent bonding. Let's get that mouse guy out of the way. All right, so covalent bonding. The valence electrons, these are the electrons from the outside. Right, so valence electrons are electrons on the outside. And co means together, right? So co is for like cooperation or doing or doing something with somebody. So co means sharing. And so covalent bonding is bonds formed when atoms share electrons. So that's a perfectly good definition. One of the things that I know, and I think you probably also know, is that this most often happens with elements on the right-hand side of the periodic table. So it's most often with nonmetals. Bonded to other nonmetals. Right?
Correct.
Okay, thanks. Why that works is because we know that those elements have close to full octets, right? And so if we look at something like a fluorine atom, in its outer shell of electrons, it has 1, 2, 3, 4, 5, 6, 7 electrons. And if you're unsure about that, let me just share my screen here for a second. So if I share my screen and I bring you over here to a periodic table, this might remind you that fluorine is in group 7, 7A, group 17 of the periodic table. That will remind us that it has 7 electrons around the outside, and it only needs 1 more electron to get to having 8, having an octet like the noble gases. So here's the fluorine, 1, 2, 3, 4, 5, 6, 7, and I'm going to draw another fluorine, and I could draw it the exact same way with its lone electron over here, but I'm going to leave its lone electron over on this side. So there's 1, 2, 3, 4, 5, 6, 7. And so if I bring my 2 fluorines atoms close enough together, these 2 electrons can occupy the same orbital, and then this fluorine will have 8 electrons, and this fluorine will have 8 electrons, and so their octets will be satisfied, their orbitals will be full, and so that will make the fluorine F2 molecule more stable, and so it will hold together as a single atom. So I'm just going to bring them just a little bit closer together. I'm going to write them all over again. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And so these 2 electrons here are shared between the fluorine. And so fluorine will form F2, fluorine gas, as a compound.
Okay, so when an electron when atoms share 2 electrons with each other, they make a covalent bond?
Right. That's exactly what they do. Yeah. And we could do a different one. This time I'm going to do it with hydrogen, which only has 1 electron, and fluorine, okay, let's go back to the periodic table again for a second. So here's hydrogen over in group 1. it only needs one electron to get to having 2 electrons in its 1s orbital. And so if hydrogen can share an electron with something else, in this case, like the fluorine, then it will have a perfectly nice pair of electrons in its orbital. The fluorine will go from having 7 to having 8, and it'll have a completed octet. And so if I bring my hydrogen atom and my fluorine atom close enough together that this electron and this electron can be shared, it will hold these 2 atoms together in the form of a molecule. And so this pair of electrons represents the covalent bond. Hydrogen fluoride. Oh, I got distracted, forgot to finish up my. And so the formula is HF for hydrogen fluoride.
Okay.
What do you think about that?
That makes sense.
So to recap, we've got hydrogen with 1 electron, fluorine with 7 electrons. The hydrogen would like to have 1 more electron. The fluorine would like to have one more electron. And so if we bring the fluorine atom and the hydrogen atom close enough together so that these 2 electrons can be shared, as shown in this picture, then we can hold the hydrogen and the fluorine together and forming a covalent bond by the shared electrons. And so we can make HF as a molecule, or nature can make HF as a molecule. And the formula is HF, hydrogen fluoride.
That makes sense. Awesome.
Shall we do one that's a hair more complex?
Yeah.
So let's do methane. And maybe we don't really know what the formula for methane is. We just know that it's carbon and hydrogen. Okay. Maybe you do, maybe you don't know. So if I go to the periodic table, I find carbon here in group 4. And so that tells me that carbon has 1, 2, 3, 4 electrons around it. It also tells me that carbon would like to get 1, 2, 3, 4 more electrons itself to get to 8. So carbon is looking for 4 electrons. And as we saw a second ago, hydrogen has 1 electron. So let's stop the share, bring it back up here. So we have carbon, 1, 2, 3, 4. It's looking, it has 4 electrons in its outer orbitals, and it's looking for 4 more. And hydrogen has 1 electron. So it's very easy to imagine that I bring those close enough together that those 2 electrons are shared between the carbon and the hydrogen. So if I do that, 1, 2, 3, 4, hydrogen and its electron, the hydrogen is perfectly stable now. It's completely satisfied. But the carbon is still short of some electrons. So if I get another hydrogen, and I put its electron right there, and I bring it in close enough and share around it, now this hydrogen is perfectly stable, but the carbon will still be short 2 electrons. You can probably see where this is going. 1, 2, 3, 4, hydrogen, hydrogen, hydrogen. Still, all my hydrogens are satisfied. The carbon is feeling still a little unloved. I bring in the 4th hydrogen, and now each one of my hydrogens has the right number of electrons, and the carbon has 1, 2, 3, 4, 5, 6, 7, 8. And so if I take carbon and hydrogen, 1 carbon and hydrogen, as many hydrogens as I need, will form methane CH4. And that's the formula for methane, formed by 4 carbon-hydrogen shared bonds.
So for covalent bonding, if we need to know how many electrons an atom needs to complete its octet, then it seems like that's how many bonds that atom can make in covalent bonding. Is that true?
Right, I think so, yes, because we know when we saw fluorine, it needed 1 more electron, it formed 1 bond. With hydrogen, it needed 1 more electron, and it formed 1 bond. With carbon, it needed 4 more electrons, it formed 4 bonds. So here is hydrogen forming 1 bond because it needed 1 electron. Here is carbon forming 1, 2, 3, 4 bonds because it needed 4 more electrons. Nice.
Anything else, Dr. Hunter?
Let's do one that is, let's do water. So water is oxygen and hydrogen. If I go to the periodic table again, here's oxygen. Oxygen is in group number 6, so I've got 6 electrons. So let me come back to my oxygen. I've got 1, 2, 3, 4, 5, 6 electrons. I've got hydrogen with 1 electron. So according to your theory, oxygen is looking to needs 2 more electrons, so it's going to make 2 bonds. Hydrogen needs 1 electron, it's going to make 1 bond. So there's a bond between the oxygen and the hydrogen. This oxygen is still not satisfied with its octet, so I'm going to bring another hydrogen in. If I bring this one in and I share around there, then I end up with oxygen, 1, 2, 3, 4, hydrogen, 1, 2, hydrogen, something like that. And that tells me that when I make water from oxygen and hydrogen, I end up with 2 hydrogens and 1 oxygen, and I form H2O. What do you think?
I think it all works out. That was good.
Let's do one more.
Okay.
Let's do hydrogen peroxide. Okay. This is harder. Exact same concepts, but it's definitely a notch harder because hydrogen peroxide is made out of hydrogen and oxygen, but it's not H2O. It's a liquid, it's clear, but it has some other properties that make it distinctly different than in fact, the formula for hydrogen peroxide is H2O2. So we've got to somehow come up with some way of putting these atoms together that will have all of the bonds satisfied. So I'm going to start by drawing an oxygen. 1, 2, 3, 4, 5, 6. And I'm going to draw a hydrogen. And I'm going to draw my other hydrogen. And I'm going to draw my oxygen. And I'm going to do everything according to the rules. And there's going to be something interesting that happens along here. So here's an oxygen with 6 electrons. I'm going to bring this hydrogen in, and I'm going to share right there. I'm going to take this electron, and I'm going to share it with this hydrogen. I'm going to bring it in like that. If I do that, If I do that, this hydrogen has 2 electrons, it's good. This hydrogen has 2 electrons, it's good. The oxygen has 1, 2, 3, 4, 5, 6, 7, 8, it's good. So we've made a perfectly good compound. In fact, you know already, we've actually just made water again. So if we connect our oxygen and our hydrogens this way, we're going to make water, and we don't have any room for this other oxygen that apparently exists in hydrogen peroxide. So this was a great attempt, but it made the wrong compound because we allowed this hydrogen to get in here on this oxygen's electron, and we have to do something different. So I'm gonna start again, and hopefully this time I'm not gonna make water. Hopefully this time I'm gonna make hydrogen peroxide. So H2O2, I've got an oxygen, 1, 2, 3, 4, 5, 6, and I got an oxygen, 1, 2, 3, 4, 5, 6, and I'm gonna go hydrogen. I'm gonna go hydrogen. And what I'm going to do is I'm going to share these 2 electrons across here, just like I did before. And then I want to share something. This oxygen needs another electron, but last time I took this one. Bad idea, because that ended up me being stuck making water. So this time I'm going to share those 2. I'm going to share between the 2 oxygens. And then I've got 1 electron left to share with my hydrogen. And so now I can count 1, 2 for my hydrogen, 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen, 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen, and 1, 2 for this hydrogen. And so I can be reasonably confident that something like that is a perfectly legitimate structure for hydrogen peroxide. And look at this. Here's my covalent bond. Here's my covalent bond. Here's my covalent bond, where the electrons are shared between my hydrogen and my oxygen, or in this case, shared between my oxygen and my oxygen, or my oxygen and my hydrogen. So we made perfectly legitimate compounds sharing those electrons between the hydrogen and the oxygen. And so covalent bonding helps explain legitimate. Oh man, I forgot. Legitimate compounds via shared electrons. What do you think about that, Kevin?
That looks good.
Do you think there's anything that we should review on that?
No, I think you explained it all.
Okay.
Yeah.
All right, so that's covalent bonding, and that was for non-metals to other non-metals, typically over on the end. So let's talk about ionic bonding and a little bit, okay?
Yeah.
Okay. So ionic bonding is rather than electrons being shared, electrons are transferred. From atom to atom. And in thinking about this, it's worth remembering that atoms are neutral. They have this, atoms have the same number of electrons and protons. And so because they have the same number of electrons and protons, they have a neutral charge. But if electrons are transferred from one atom to another, so if I have a sodium atom, which has a bunch of electrons, and then, oh, let's go look at the periodic table again for a second. If I find sodium over here in group 1, that reminds me that sodium has 1 electron in its outer orbital. So sodium has 1 electron out here. And we're going to take that electron and we're going to transfer it from the sodium atom to some other atom. And in my case, I'm going to transfer it to a fluorine. So let's have a quick look at the fluorine again. So I'm going to transfer that electron from my sodium over here to the fluorine. And the fluorine currently has 7 electrons. And by transferring it, it'll have 8 in its outer orbitals. So I'm going to transfer it. It has 1, 2, 3, 4, 5, 6, 7. I'm going to transfer this electron from my sodium over to my fluorine. So I'm going to draw a little line saying it's going over there. And as soon as it does that, my sodium is going to go from being sodium neutral to being sodium with a positive charge. And my fluorine is going to go from being neutral fluorine to fluorine with a negative charge. So in ionic bonding, electrons are transferred from atom to atom. So we've had the electron transfer, and what results is a sodium with a positive charge and a fluorine with a negative charge. And because they have opposite charges, they're attracted to each other. And because they're attracted to each other, then they are held together, sodium plus, fluorine minus. And so we make the compound sodium fluoride by having that electron transfer. So this makes sodium fluoride. What else should I say about this, Kevin?
So, could you explain to me a little bit about the difference between covalent and ionic? Clarify that a little bit, because they both kind of seem similar.
Sure. I think they both result from similar desires. So they both result from similar desires. In both cases, atoms are attempting to fill outer orbitals. In the case of hydrogen, it has 1 electron sitting in a 1s orbital, right? Sitting in that lowest energy level, and it is trying to end up with a 2nd electron in there. In the case of fluorine, it's got 7 electrons, and it's trying to end up with 1 more electron, and it's trying to end up with 8 electrons. In case of sodium, sodium has 1 electron in its outer orbital, and it's trying to empty that one out so that it has 8 electrons inside. In the case of oxygen, 1, 2, 3, 4, 5, 6, depending on how we draw it, it's trying to get 2 electrons to fill those 2 spots. So the covalent bonding, the atoms share electrons to fill those locations. In ionic bonding, an electron is transferred from one atom to another atom.
So the difference between the two is whether or not they're sharing electrons, basically.
I think so. I think so. Is there a sentence that I'm missing in there that you think needs to be said?
I don't know if you mentioned this. Ionic bonds are typically between metals and non-metals. I don't know if you mentioned that.
I'm not sure if I did, but certainly that's a really good point. That in terms of the overall compound formation, there is that if you have metals bonding with non-metals, they don't do a very good job of sharing electrons, that the fluorine, for reasons that will become obvious through the non-metals are more attracted to those electrons, and so they're pulled towards the fluorine more, and so the non-metals take the electrons all the way away from those metals, and so the fluorines end up with, the non-metals end up with an overall negative charge, and the metals end up with an overall positive charge. Yeah, so ionic bonding is typically between metals and non-metals.
I think that covers all the bases. Is there anything else?
I don't think so. I think we're good in terms of that.
Okay, awesome.
Okay, thank you very much, Kevin.
Thank you, Dr. Hunter.